While agriculture plays a critical role in supporting the growing global population, it also requires significant energy inputs. Modern farming depends on both direct energy, such as fuel for machinery, irrigation systems, electricity, and human labor, as well as indirect energy, which includes the energy used to produce fertilizers, pesticides, seeds, and other agricultural inputs. As the food demand increases, the energy inputs for agriculture also grow significantly in order to maximize crop yields and reduce labor costs. Therefore, in order to evaluate agriculture sustainability, the concept of energy balance must be considered. This concept compares the total energy invested in production with the energy contained in the agricultural products generated. This allows researchers to understand if any energy efficient improvements are required. Because the excessive use of energy in agriculture can have serious environmental impacts, it is crucial to minimize it. This is the case as it can contribute to soil degradation, water contamination, greenhouse gas emissions, and biodiversity loss.
Agriculture first began about 12,000 years ago when humans shifted from nomadic lifestyles to permanent settlements. For most of the pre-industrial period, farming relied on human and animal labor, with nutrients continuously replenished through manuring and crop rotation, and maintaining high energy returns without degrading the land. This balance shifted during the 20th century as rapid population growth prompted the widespread adoption of synthetic fertilizers, fossil fuel-powered machinery, and pesticide-dependent monocultures. While these technologies increased yields, they introduced substantial fossil fuel consumption at every stage of production, declining the agricultural energy returns from roughly 5 in the early 1900s to below 1 in many industrial systems today. The environmental consequences are already evident. Fertilizer runoff creates eutrophic dead zones, irrigation withdrawals deplete water supplies faster than they recharge, and intensive farming degrades soils, reduces biodiversity, and threatens future yields. With agriculture accounting for about 18.4% of global greenhouse gas emissions and the UN projecting about 10 billion people by 2050, these pressures will only intensify. To meet our needs without compromising future generations, larger-scale policies must rapidly integrate adaptive measures accounting for regional differences, small-scale stakeholders, and climate-related strategies.
Those who oppose sustainable agriculture often rely on utilitarian philosophy, which prioritizes maximizing overall benefits. In the context of agriculture, this means producing enough food to feed the largest possible number of people. As the global population continues to grow, opponents argue that increasing energy inputs, such as pesticides, is necessary to maximize food production, even if they lead to irreversible environmental damage. Supporters of sustainable agriculture may adopt an anthropocentric perspective. In this view, humans have a moral obligation to protect the environment because environmental damage can harm human well-being, for example, through pollution. This ethic is derived from philosophers such as Aristotle, who argued that nature exists for human purposes, and Immanuel Kant, who suggests that cruelty toward nature may encourage cruelty toward other humans. Therefore, protecting the environment is considered morally important, not because it has worth, but because it benefits humans. In contrast to the anthropocentric view, the ecocentric perspective gives moral value to the environment itself. In this approach, moral consideration is extended to living and non-living beings, and humans and nature are seen as interconnected rather than separate. In general, they oppose intensive agriculture as it does not maintain the integrity, stability, and beauty of the biotic community.
Recent news coverage highlights how energy-intensive agriculture can impact the environment negatively. One widely reported example is the Gulf of Mexico dead zone. According to the U.S. National Oceanic and Atmospheric Administration, fertilizer runoff from large-scale farming in the Mississippi River Basin leads to large algal blooms that remove oxygen from the water, harming the ecosystems. This shows how energy-intensive inputs like synthetic fertilizers can create major environmental consequences. At the same time, many news outlets report on the growth of precision agriculture technologies. For example, Reuters has reported that farmers are increasingly using GPS-guided tractors, drones, and soil sensors to apply fertilizers and water more efficiently. These technologies reduce unnecessary energy use while maintaining crop yields.
Now, what are the roles of engineers? Engineers must redesign technologies to improve efficiency and sustainability. The types of technologies can be illustrated through this simplified diagram. First, we have precision agriculture systems mentioned in the previous slides. Second, remote sensing technologies like satellite imaging systems that can help detect issues and diseases early on. Third, biotechnology like gene editing that enables the development of pest-resistant crops. And lastly, we have IoT and automation systems that can improve productivity and resource management by allowing real-time monitoring and automated farming operations.
Engineers must also manage risks and ethical challenges. In many developing regions, farming is dominated by smallholder farmers who cannot afford advanced digital tools. Engineers therefore have a responsibility to design affordable and scalable solutions so these farmers are not excluded from innovation. Furthermore, to prevent equipment failures, data breaches, and inaccurate AI predictions that could harm farming operations, engineers must design reliable and secure digital farming systems. So to wrap it up, the next steps are 1. Expand research in smart technologies. 2. Adapt the technologies to the conditions of developing countries. And 3. Technology alone will not solve the agricultural energy imbalance. Collaboration between engineers, farmers, scientists, and policymakers must be encouraged to develop effective solutions. Ultimately, as the global population grows and agriculture requires increasing energy inputs, engineers must help improve the energy balance of food production while protecting the environment.